Let's begin with one population, say our source population. Our basic population growth model requires that we have some information about our BIDE characteristics, our births, immigration, deaths, and emigration. And so we have some raw numbers here that we can use. However, raw numbers don't have a lot of utility in modeling. We can't make a lot of assumptions about them. They simply are numbers. And so to address this issue, to improve our ability to do some modeling here, we oftentimes take those numbers and convert them into per capita rates. And per capita rates are like individual rates here. So that might be for births, for example. That might be the number of births per individual in our population per unit of time. And so these are per capita rates for each one of our BIDE characteristics. So we'll go through how to calculate those per capita rates. We'll then insert those per capita rates into our model here. So we'll substitute them into where we would have values, number values for our BIDE characteristics. And then we'll spend a little time refining and simplifying our overall equation here. And we'll do that by bringing in a couple of new terms. We'll bring in the term R, and we'll bring in the term lambda. So let's get started. We'll begin by calculating per capita rates. And per capita rates are really pretty easy to calculate. So our per capita rates we're going to define by lowercase letters. So these are our BIDEs, but we're now using lowercase letters. And the T just indicates that that's our time period that we're interested in. And all a per capita rate is the number of births, in this case, divided by our population size. So it's just giving us a measure of the number of births per individual. And we can simplify that a little bit more. So we could define BT as, if we cross multiply here, as BT times NT. In other words, the number of births occurring in a population is our rate, our per capita rate, times our current population, right? So the number of individuals that we've got. So let's do the same for immigration. So that's just the number of immigrations divided by the population size. And then we'll do it for deaths, so number of deaths divided by the population size. It's getting a little tight here, so we'll move here and I'll say number of immigrants divided by population size. So we'll simplify them a little bit more. I know this is getting a little complex, but we should have, in this case, our number of immigrants being our rate times our population size. And for deaths, our raw number being our rate times our population size. And then lastly, our immigrants being our rate times our population size. Make sense so far? Easy enough, really easy to derive these values. Now, so we've got per capita rates. The next step is we are going to substitute those per capita rates into our equation. So what we're trying to do here is take our basic equation that describes population growth or population change and really sort of distill it down and simplify it a bit more. And so the rates really help us to do that, and I think you'll see why in a few moments. So let's substitute those values in. This is our basic population growth model that we introduced earlier. And that gives us, of course, the number of individuals in our population, plus now I'm going to substitute in our rates from the previous slide, times NT, plus I times NT, plus deaths times NT. I'm sorry, that should be minus our immigrants. Let me just change that symbol here. Okay, make sense? So all I've done is just substituted in our rates for our raw numbers. Okay, so we'll go a little bit further here. And what I'm going to do is just take out, I'm going to factor out an NT. So this is just going to simplify our equation a little bit more. So I'm going to take out NT, and that gives us now B plus I minus D minus E. Got it so far? Times NT. So I do that because this expression here is something that we call R. And R is oftentimes referred to as the geometric rate of increase. And you might have heard that term before, the geometric rate of increase. So we've got R here, and I'm going to just substitute R in now to represent this term. So one thing about R is that we know R represents a measure of growth from one time period to the next. And R is really centered around 0. So a value of 0 for R would indicate our population doesn't grow from one period to the next. If R is above 0, if it's positive, that it will in fact be growing. If it's negative, it will be declining. So I'm going to now take this expression and I'm going to move you to the next slide here, and there it is. So all I've done is taken this equation here, in which we've got NT plus R times NT. So let's have a look. We've got NT plus 1 equals NT plus R times NT. Wow. Sounds complicated, but I assure you things will get a little bit simpler. So what we're saying here is that our population one time step into the future, NT plus 1, is our current population size plus our population size times our geometric rate of growth. And so that should give us a new value for the next year. Could be positive, it could be negative. So we can further distill this down a little bit more just for fun, but what I should say is that I'd like you to remember this equation here, because we'll come back to it in just a few moments. So remember this equation. So we can simplify here, we can simplify this equation, and what I'll do is I'll subtract now NT from this side and bring it over to this side here. So I'm subtracting from both sides. So now we've got NT plus 1 minus NT equals R times NT. Okay, so what this is really a measure of the change in population size. It represents the change. So if we have a certain number of individuals in the next year minus the individuals we've got this year, that gives us a measure of that change. So we can call this the measure of change in our population, and that will be then R times NT. And we'll go one further step. We could say the change in our population divided by our current population gives us a value of R. So I've just divided here NT. Lots of movement of these variables around, but essentially what this equation is telling us is that R also represents our change in population per individual. So this is simply a per capita rate of change in our population. And R can be expressed this way, can also be expressed as a function of our BIDE characteristics, which we saw before. Okay, so I'm going to jump back to this equation here, the one with the star. In this equation, which we see here, which is a more simplified form of our original model, we are going to introduce one more term here, and that's called lambda. And so I'm going to do that by factoring out NT from the right side of our equation. So that gives us 1 plus r times nt. So that 1 plus r term is given its own symbol, which we call lambda. And that lambda is sometimes referred to as the finite rate of increase, which you might have heard before. So that's our lambda value. And I'm going to just substitute that lambda in. So we have lambda times nt equals nt plus 1. Well, that is a lot here to cover. And to give it some perspective here, what we're essentially saying is that if we want to understand or to model the change in a population from one time period to the next, we can do that if we know, for example, our current population size. If we have our current population size and we also know something about our BIDE characteristics for that population size, we can then estimate how we expect the population to grow into the next period. So if we have our current population size and our BIDE characteristics, with our BIDE characteristics we can estimate rates, and we can substitute those rates into our basic population equation. With that we can derive r, and with r we can derive lambda. And if we have lambda then, which is another measure of the rate of growth of a population then, we can project how the population will change from one time period to the next. So if we're dealing with our source population and we know what lambda is based on our BIDE characteristics, and we know what our current population size is, if we multiply one by the other, that will tell us then what we expect our population to be like one time step into the future. And in fact, we could do that again. We could go one time step into the future, and if we had lambda, we could estimate what we expect lambda to be like at nt plus 2. Let's now return to sources and sinks. Remember, a source population has greater births than deaths. So what would our lambda value be for a source population? Our lambda, of course, would be positive, so it would be greater than 1. For our sink population, remember, we have greater deaths than births, or fewer births related to deaths. What would our lambda be in this situation? Here we would expect our lambda to be less than 1 in value. So for our source population to be in an equilibrium state, in other words, for our source to be unchanging from one year to the next or one time step to the next, to be in equilibrium, it needs to be exporting individuals. So again, you can imagine a source population that grows and grows and grows. It's on an upward trajectory. It has a positive greater than 1 lambda value, and it reaches a point at which carrying capacity is attained. And at that point, it needs to start sending individuals out in order for that population size, really a carrying capacity, to maintain from one year to the next in equilibrium. So what about our sink population? For our sink to be in equilibrium now, our sink population needs to be accepting individuals from perhaps our source. So for it to be stable from one year to the next, it needs to be receiving a certain number of individuals. Again, a certain number to be in equilibrium. So if we have this condition, then consider our greater population. Our greater population size, which we're probably most interested in, is really, again, a balance between the surpluses in our sinks and the deficits that occur from our sources. So I'm going to pass you over to my colleague Terry. Terry will build a spreadsheet that will model a source population, model a sink population, and explore the dynamics between these two and how they play out in terms of the population size of the greater population and how we can estimate or project that greater population into the future. So Terry, on to you.